This week's topic is the theory of continental drift and plate tectonics. This is a theory that the Earth's crust is made up of about 13 pieces called tectonic plates, and it is the study of what happens when those plates move and interact. The theory of plate tectonics is considered one of the most important concepts in earth science because it is a unifying theory. This means that it ties other concepts of earth science together. Before this theory, scientists studied rocks, mountains, earthquakes, oceans, and volcanoes, but never realized that all these things were closely related. It wasn't until a German earth scientist named Alfred Wegener was staring at a world map when he noticed that South America and Africa looked like they could fit together like jigsaw puzzle pieces. He decided to set off on a journey across the world to investigate this theory to see if it really was just a coincidence. Over the next 3 years, he explored South America and Africa and found many pieces of evidence to support his theory. First, he found fossils of remains of a rare extinct dinosaur named Mesosaurus in both South America and in Africa. He then found rock formations in South America lined up perfectly with rock formations in Africa. And finally, Wegener found that evidence of glaciers in warm tropical regions of Africa, and he found fossil evidence of tropical plants in the cold Arctic regions of Greenland. He had enough evidence and decided that this wasn't a coincidence and that he was going to publish his theory. He called this theory continental drift. He suggested that all the continents had once been assembled in a great mass called Pangaea, which means all Earth. He suggested that the continents had slowly moved apart over time. So, exploring the geologic history of New York State on page 8 and 9 of your reference table, notice first that as this is assembled with the top being the present and the bottom of your reference table being the past. In the first column, it breaks into largest time differences, which are eons, and we have the Precambrian, and then we have the Phanerozoic. And then the rest of the Earth Science reference table just basically focuses on the Phanerozoic, and you can see here that it breaks the Phanerozoic into 3 eras: the Cenozoic, Mesozoic, and Paleozoic. Those are further broken up into periods, and then finally into epochs. And you can notice in that column with the epochs, it also tells you how many millions of years ago each period started. If you want to find out something on this table, you can look, for example, at the Cretaceous, and if you want to find out information about what was happening in terms of life on Earth or important geologic events, you just follow that row over to the right. If you follow it all the way over, you can actually see how the continents were positioned during that time. The scientific community did not support the Alfred Wegener's theory because he couldn't answer one important question: what makes the continents move? Alfred Wegener decided to set out again to collect more evidence on his theory. While traveling in Greenland to gather more evidence, Wegener was caught in a terrible storm and froze to death at the age of 49. It would be more than 20 years before the scientific community realized that his theory was actually correct. Alfred Wegener couldn't explain what made the plates move. Today we know that heat from deep inside the Earth moves the plates by convection. We can see here that heat from deep inside the Earth warms up the magma underground, making it less dense, and this causes it to rise. As it rises, it moves away from that heat source, and this causes these circular convection cells. This is not at all unlike what we studied earlier in the year when we looked at how hot water creates this circular motion. Notice also on page 10 that oceanic crust is denser, and so it always subducts underneath the continental crust. You can also notice in this diagram that oceanic crust is also thinner than continental crust. On page 5 of your reference table, we have this map of tectonic plates. You can see in kind of a grayish blue color we have the outlines of the continents, and then the black we have the borders of these plates. Notice that the map symbols are used to identify how the plates are moving. There are 3 main categories of plate boundaries: divergent, which is where 2 plates are spreading apart; convergent, where they're coming together, and transform, which is where they're sliding past one another. Divergent plate boundaries, plate spreads apart, hot material pushes up through and creates new crust. This was first proven in some investigations exploring the ocean floor after World War II. It turned out that throughout Earth's history, the magnetic field of the Earth has changed many times, and so as this new crust was created, we had magnetic direction of different minerals was aligned in different directions, and this helped us figure out that the oldest rock was furthest away from the spreading center inside the ocean. The second kind of boundary we will investigate is a convergent boundary. And here we have a sequence, first, second, third as you go down. In the first sequence we have plate A and plate B coming toward one another. Over time, plate A may subduct underneath plate B. Notice that plate B, the oceanic crust, always goes underneath the continental crust because it's more dense. And where that subduction happens, we have the formation of a deep ocean trench. And where that plate is melting, that hot magma often works its way up through the rock and creates volcanoes and the igneous rocks underground if that magma never reaches the surface. Finally, when these two continental pieces of crust finally collide with one another, it often creates very large mountains, not unlike the Himalayas, where two continents are colliding. A part of the Earth's crust where magma actually breaks through is called a hot spot. This could be because the crust is a little thinner, or as we saw before, it's just a lot of hot magma from melting material that works its way up. The thing is that the hot spot often stays put while the crust moves over the top of it. And this can often cause a volcanic island arc, which is when you have a bunch of islands poking out through the ocean all in a row. Hawaii is an example of an island arc caused by volcanoes. And you can see where as the plate moves, in this case, in a northwestern direction, the hot spot stays put, and so we have these older volcanoes further away from the hot spot, and the newest volcanoes are the ones that are closest to the hot spot. Finally, we have transform boundaries, and this is where plates are sliding past one another. And the best example of this that we're familiar with is in California. We have the San Andreas Fault, the Pacific Plate and the North American Plate are sliding past one another, and that's the reason that we get so many instances of earthquakes in California.